and let us begin. So in today's lecture, we should be talking in detail about two other methods of drug design, which you can use for identifying or identification of potential ligands of your target. Yeah. So of course you already know one method which you can use to identify new potential binders of your target, and it is molecular docking. Yeah, but molecular docking, although quite precise, it takes quite a long time, a relatively long time to perform. Yeah, you already have some experience with the docking, so you have the idea about the time scale, and I can tell you that, for example, if you are using a normal computer or laptop, it will take you usually 30 seconds up to 1 minute to dock one compound. Yeah, so let's say if all goes well, you can do 2 compounds per minute on a single node on a single CPU of your computer. This is not bad, but when you want to do really high throughput virtual screening, this is simply not enough, because if we are talking about real high throughput virtual screening, we usually start from at least 100,000 of compounds, if not millions of compounds of potential ligands. So we have very large libraries which we have to screen by in silico methods, and so that's why we need faster methods, yeah, to identify potential ligands. Faster methods which we can employ in the beginning of the HTVS scheme. Yeah, so we will use these fast methods to cut down the library of potential ligand, and then when the library is cut down to reasonable numbers, like thousands or tens of thousands at maximum, we can use the molecular docking. So today we will be talking about two methods which are significantly faster than molecular docking. And first method is called Pharmacophore searching. So we will be doing a search based on Pharmacophore models. And the second method, which is even faster, is searching of potential ligand based on molecular similarity. And to determine whether two molecules are similar, I mean structurally similar or not, we will use so-called molecular fingerprints. So we will have a word on this in the second part of the lecture. Okay, first let's focus on the Pharmacophore models and searching based on Pharmacophore models. Pharmacophore-based searching. So firstly, we should define what it is a pharmacophore. Yeah, so probably you have heard this term before, for example, in the pharmacology, yeah, or even in medicinal chemistry. So pharmacophore is basically a set of features, yeah, and by features we usually mean some atoms or functional groups, which are orientated, which are somehow placed in the space, and these atoms or functional groups are necessary for the interaction with the receptor. Yeah, so pharmacophore is a set of features which are necessary for the interaction. It means binding to the receptor. All right, so this is a very simple definition. Yeah, here I will remind you of the other almost opposing term which we used in the last lecture when we were talking about de novo design methods, and we were talking about scaffold method, which is called scaffold hopping. So if you remember, scaffold, on contrary, was a part of the drug which does not perform any significant interactions with the receptor. Yeah, it just works as a skeleton to which the important groups are bound. Yeah, so we have this skeleton which we call scaffold, which we can replace by scaffold hopping, and then we have the features which are important, and these important features are pharmacophores. Yeah, so the pharmacophore is not only a list of features like 2 hydrogen bond donors, 2 hydrogen bond acceptors, aromatic ring, and so on, but it's also their mutual position in space. So you have to identify coordinates in the space. And this is a 3D pharmacophore. Okay, before we can perform a searching based on pharmacophore, we first need to define the pharmacophore. There are several ways how to define or how to construct a pharmacophore, and we will be talking about 3 of them. The first one, which I have here, is the only one which is direct, which is so-called direct method. So it is the optimum situation when you are happy and you can find in the PDB database or other crystallographic database, you can find a structure, experimentally determined structure of ligand receptor complex. Yeah, so you have your target, 3D structure of your target with bound ligand. So it's quite easy situation for you. So you will just have a look at the interactions which are being observed between the ligand and the receptor. And based on these interactions which you observe, you will construct the pharmacophore model. So this approach definitely belongs to structure-based drug design methods. Yeah? If you remember, structure-based drug design methods are methods for which you need to know the structure of the receptor, which is exactly this case. Then we have 2 indirect methods how to determine a pharmacophore. Situation number 2 is that we have the crystallographic structure of the target. So we know where the binding site is, or we can at least guess from literature or using the application site finder, which I presented to you on the last seminar. Yeah, so we can have the information about the binding site, but there is no ligand. So what we can do, we can just observe how the binding site looks like. For that, we can use the different colorings of the maps, which we also practiced in the last seminar. And based on these features, like say, the amino acids and the pharmacophore features, which we observe in the binding site, we can just roughly guess which interactions might be important for the possible ligands. Yeah, so we cannot be sure because there is no ligand. We can just select basically randomly based on our experience some features which seem to be quite important. So we are never sure about this model, but it may work. Situation number 3 is also an indirect method, and in this case we are even less happy with the situation. We do not have the structure of the complex. We neither have the structure of the target. We only have the list of active compounds, which we know from the literature, for example. So what we can do, we can perform so-called flexible alignment of small molecules of the ligands which are active. And then we will observe which features in these active molecules are repeating and overlaying in most of the active compounds. Yeah? And from this, we can somehow deduct that the repeating features, the features which are repeated heavily within the active compounds, might be important for the interaction, so they might be part of the pharmacophore. So from this information, we can build the pharmacophore model. This scenario number 3 would definitely belong to ligand-based drug design methods because we do not know the structure of the receptor. It might be quite intriguing for you to hear that I told you that using method number 2 and method number 3, we can be never sure about our pharmacophore model. So how can we know that our pharmacophore model is correct? Well, we can definitely construct more of the models because, as I told you, searching using pharmacophore models is quite fast. So you can easily allow yourself to construct more than one pharmacophore model and test all of them. And the final testing condition is whether the model will be giving good predictions. I mean predictions which are consistent with the experiment. Yeah? So if the pharmacophore model will be able to predict active compounds and distinguish active compounds from inactive ones. Yeah? And because pharmacophore searching is quite simple, you can easily construct more models, test them all, and then select the best one. All right. Now, before we get to the individual situations, scenario 1, 2, and 3 in more details, I would like to have a brief talk about the specific pharmacophore annotations or pharmacophore features, if you want to. Okay, so there are three main categories, and we are asking you this in the final test for, in this subject. So there are so-called atom annotations, or we can call them also point annotations, which mean that the annotation is located directly on an atom. Yeah, so it can be something like H-bond donor, yeah, because H-bond donor is associated with a distinct heavy atom. It can be H-bond acceptor, it can be cation, it can be anion, and so on. Here, an important notice when we talked about H-bond donor feature, the annotation is always put on the heavy atom. Yeah? So if you imagine, for example, I don't know, hydroxyl group OH as the H-bond donor, yeah, the point annotation is always put on the heavy atom, on oxygen, not on hydrogen. I will show you on the next slide. Why is this the common situation? Maybe you remember that when we talked about the crystallographic structures, I pointed out that in the vast majority of crystallographic experiments, you do not see the hydrogens. So the position of hydrogen atoms is only calculated from the software. Yeah. Okay, I hear some beeping in my Teams, so I'll just check if someone is not in the. Yeah, looks okay. Okay, so we can continue. All right, so the next type of annotations are centroid annotations. And this is quite nice feature. So when you have several atoms, like let's imagine, for example, cyclohexane ring, yeah, cyclohexane ring or benzene ring. So if you have cyclohexane, of course, all 6 carbon atoms are hydrophobic. Yeah? So you can denote these 6-point annotations for 6 carbons, but by this annotation, you would ask the computer to search for potential ligands which have 6 hydrophobic atoms. Yeah? But this might be too restrictive. Maybe you would like to be a little more benevolent. So what we can do, we can construct a centroid annotation, which will be put not on each of these 6 atoms, but just in the middle, in the geometric center of these 6 carbon atoms. And this tells the computer, okay, find ligands which have at least 1 hydrophobic atom somewhere in this area. I will show you on the next slide. And then the last category are projected annotations, which means that we are not describing only the position, but also the orientation. So the direction, actually, the direction from which the expected interaction is going to take place. I will show you on the next slide. So on this slide, I will describe different versions of Pharmacophore features to you, and I think you will simply get the differences. So first of all, we can be annotating many of the Pharmacophore features. So this window is a direct screenshot, or cut from the MOE software, so the software which you will be using, and nothing much surprising. Yeah? So you can imagine that Pharmacophore features can be anions, cations, H-bond donors, H-bond acceptors, metal ligators. Okay, metal ligators, this might be a little surprising for you. What do metals have to do with protein activity? So here I have to remind you that many receptors, and especially proteins, contain metal ions, metal okay, yeah, metal ions, that's what I want to speak about, as cofactors. Yeah, so we call these enzymes metalloenzymes. So the metal ion is usually somewhere in the active site and important for the catalytic mechanism of the action. So the quite common situation is that the ligand, let's say inhibitor, have to somehow interact with this metal. Yeah, so that's why some ligands have to have metal ligating pharmacophores or metal ligating functional groups, let's say. Okay, let's continue. So aromatic centers, yeah, hydrophobic centers, and so on. So these are the types talking about the quality. And now if we should talk about the type of annotation, so let me demonstrate the difference between point or atomic annotations, then vectors, yeah, and the centroids. So for example, let's look here. So here we have an amino group, which definitely can act as a donor, yeah? Donor, H-bond donor. So we can use a point annotation, atom annotation, and put the feature here. So this would be the atom or point annotation of donor. Please note once again that we do not put the annotation on the hydrogen, which actually is the donor, but we put it on the heavy atom, on the nitrogen. Yeah? So if we use this point annotation, we are telling the software find ligands which have donor functional group somewhere here, the heavy atom. We are speaking about the heavy atom. Yeah? But we aren't specifying from which direction we are expecting the H bond to occur. So if you want to be more specific and determine not only the position of the H bond accepting group, donating group, but also the direction from which should accept the to which it should donate the hydrogen bond, then you need to use these vectors. Yeah? So this is the vector, and this is the vector annotation. Please notice that it also always ends with 2. So don is like donor, it's the H-bond donor, and don2 is the projection of the donor feature. So what it means, you can also look at it from the point of the receptor. So donor projection, donor2, means that somewhere here, the protein, the target, should have H-bond acceptor, all right? So at this distance. So for example, carbonyl, oxygen atom. All right, or it can be here, yeah, because obviously this amino group can give the hydrogen bond in 2 directions. Yeah? This is just in the direction of the sigma bond and H bond. All right, so this is the difference. So if you are happy and if you want to have more compounds, more hits, you will just define the position. If you want to be more precise, you will also define the direction from which the interaction should come from. Very similar situation. If you look at the other side of the molecule, here this is a tetrahydrofuran ring. Here this oxygen atom can act, of course, as H-bond acceptor. So if you don't care from which direction the interaction will come, you just use this point or atom annotation. If you want to be more specific and determine from which directions the H-bond should come, and this is, of course, consistent with the location of the lone electron pairs, which are here and here. So then you also, again, have to use the vector projections. So ACC2 is the projection of H-bond acceptor. So here it means you would expect the protein to have H-bond donor. Yeah? And by H-bond donor, we mean the heavy atom. So for example, if we were talking about a hydroxyl group in the protein, here you would have oxygen, and somewhere in the middle here you would have hydrogen, and here would be the double bond. All right, so this is the difference between point annotations and vector annotations. Now let's talk about centroids. Okay, so this is the situation. We have in the tetrahydrofuran ring, we have 1, 2, 3, 4 hydrophobic carbons. Yeah? So we can do a setup of the pharmacophore feature, which would be similar to this. So here we are telling the computer, because we have identified each of the carbon atoms to be a center of hydrophobicity. So by these point annotations, we are telling the software, okay, find ligands which have hydrophobic atom here and at the same time here and at the same time here. Yeah? Here we did not want to be that restrictive, so we do not want to be looking only for ligands which have 4 different hydrophobic atoms. So instead, we produce a geometric center. Yeah? So this point is roughly at the geometric center of these 4 atoms. And we are telling the computer, okay, I don't mind whether the hydrophobic atom is here, 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 it just has to be somewhere here, and I'm happy with that. So this is the difference. Similar approach. Again, centroid annotation. So here we have the benzene ring, which is aromatic feature, of course. So if you use this centroid, which represents the pharmacophore feature, you are telling the computer, okay, find ligands which here at this point have the center of the aromatic ring. But nothing more. You are not restricting the rotation of this plane. So this the ring, the phenyl ring, can be rotated in any of possible planes. If you want to be more specific and you want to determine what should be the rotation of the benzene ring, because this of course corresponds to the pi-pi interactions which it can form, you again have to use the vectors. So this pi n would be the projection, which is the vector we are talking about is actually perpendicular to the plane of the p electrons. So you have the p electrons here in the plane, and this vector is perpendicular to it. And we are expecting pi-pi interaction from the protein to come from this side, for example. All right, so I hope you now understand the differences between point annotations and vector annotations. So if you use point annotations, atomic annotations, you are just saying where you expect the functional group to be. And when you use the vector annotations, you also say something about the orientation. It means from which direction you are expecting to have the interaction. And we talked also about the centroids. All right, so this slide I have already described it by my own words on the previous one, so we can skip it. All right, so now once we have defined the pharmacophore features and how we can define them, let's talk a little bit in detail about the three scenarios we were mentioning. So the first scenario was a direct method when we had the ligand receptor complex crystallographic structure. So the situation seems favorable, although we still have to bear in mind that we might be misled in some situations. For example, imagine a situation that you have a crystallographic complex of your receptor with ligand, but there's only one in the PDB database. So it means that you will produce the pharmacophore based on the interactions for that ligand which you observe, but it does not mean that there might be existing other ligands, structurally diverse ligands, structurally diverse to the original one, and they might have a little bit different interactions. So always bear in mind that if you use a certain ligand for the construction of the pharmacophore, you are always restricting the pharmacophore, and you might be missing other possible ligands which have different structure, for example. So this is one thing. And the other thing that when you only use one crystallographic structure, one crystallographic complex to determine the pharmacophore, you again are not covering the receptor flexibility, the flexibility of the binding site. So to cover the flexibility, you have several choices. You can either use more of crystallographic structures, more crystallographic complexes, if you have them. So in this approach, you suppose that each crystallographic complex is in a little bit different conformation, talking about the binding site, or if you have only one structure, you can, for example, run molecular dynamics simulation, which can produce different conformations of the binding site for you. All right. So the typical workflow when we produce pharmacophore from a ligand target complex. Okay, so as first point, as you would expect, you have to download the structure of the complex and prepare it. Similarly, when you prepare the complex for docking, it means you will add hydrogens. You will optimize the hydrogen bond network using Protonate 3D, for example, in the MOE software. You will correct the errors which might intrigue your results, so mainly the errors which are in or close to the binding site. Yeah? Then after these corrections, you will observe the interactions which you see, the interactions between the ligand and the target. Yeah? And from these, you will select the important ones which might form the pharmacophore. What is good about constructing a pharmacophore from a protein, so either a target or ligand target, is that you can use so-called volumes. You can, for example, define excluded volumes, which are volumes or spaces which cannot be occupied by your ligand simply because they are already occupied by the protein. So there will be a steric clash. So I will demonstrate this on the next slide. Okay, so when you define the features based on observed interactions, plus usually we use the volumes because we can take advantage of that, then you are going to evaluate the models. So evaluating means testing if active compounds fit into the model and inactive do not fit. Yeah? And it's usually an iterative process. So if you are not satisfied how your pharmacophore model distinguishes between active compounds and inactive compounds, you just do some corrections to the pharmacophore model. You can omit some features, add some features, and so on. So we are basically getting here, and by recycling this scenario, you are trying to find the optimal pharmacophore model. So here I have a slide to demonstrate how we work with the observed interactions while building the pharmacophore model, but probably I would rather switch to MOE window and I will show you online. So here we are looking on the human prolyl tRNA synthetase enzyme. The name is not important. We just have an enzyme with its inhibitor. Yeah, so there is a compound, small compound bound inside. So we can observe the interactions. Yeah, so if you look closely, so we have several hydrogen bonds. Please disregard this one because this is obviously intramolecular H bond, which is inside of the ligand. So it's not interaction with the protein. We are not interested in it. But we have one H bond interaction here. So here the ligand acts as a donor. Important thing I forgot to mention is that these donor acceptor annotations are always taken from the point of view of the ligand. Yeah? So when we see acceptor, it means ligand is the acceptor, protein is the donor. Yeah? If you see donor, it means ligand is the donor and protein is the acceptor. All right, I'll remind you on the next slides once again. So here we have a H bond donor. Here this nitrogen is an H bond acceptor, and this N4 is also an H bond acceptor from this hydroxyl group of the protein. Yeah? In theory, we might have H bond here as well, but this is much weaker, as you can see. So by the energy, so we will disregard this one. All right. So now we have defined the interactions which we observe. We can also see one more interaction which is not depicted here, but if you look at the planes of this pyrazine ring, which is heteroaromatic, and the plane of this phenylalanine amino acid, they are obviously in a good mutual position. It means they are in the same, not same, but the planes which have the same direction. Yeah, so they can form pi-pi bonds, pi-pi interactions. So we can, of course, have a look at the 2D diagram. Yeah, so this is in 2D what I have been talking about. So we have this H bond, which will be important for us, this H bond, and this H bond. We'll probably omit this one, but we can decide. As I said, you might construct different pharmacophore models and then test them all. All right, and this is the pi-pi interaction, yeah? Pyrazine to the phenylalanine aromatic ring. All right, so once we have observed these interactions, let's construct the pharmacophore model from that. So we go to compute pharmacophore query editor, yeah? And you see that once you have the query editor window, popped up, it automatically starts to suggest the potential pharmacophore features to you. Now I will try to explain why is it so good that you have the structure of ligand receptor instead of the ligand itself, ligand alone. Now imagine for a while that we do not have the structure of the complex, but we only have the ligand. Yeah. So okay, the software tells keeps suggesting some of the pharmacophore features, but we cannot distinguish which are really important and which are not. Yeah? So for example here, I could be misled by thinking that this H-bond acceptor might be important for the interaction, yeah? Which is not the case. Because if I turn on the protein again, you see that in the protein, here is no donating atom. Yeah? So obviously, this should not be the pharmacophore feature. Yeah? On the other hand, this one is quite consistent with the interactions. So let's now define the pharmacophore features. So okay, I would like to define this atom as H-bond donor. Okay, so we just select it and you click on the feature button and it will create the feature. So this is the position of the expected H-bond donor atom. The annotation is not precisely a point because you always have some tolerance. Yeah. So the tolerance can be controlled here. So by default, with the donor, you have the tolerance of 1 angstrom. So it means that the H-bond donating atom can be here or somewhere inside of this ball, of this sphere. Yeah. You can modify the tolerance if you want to, but the default value is usually a good choice. Now we have defined only the position, but we have not decided on the direction. So if I want to be more precise and tell the computer that I'm expecting the interaction from this direction, yeah, which is really the case, so I should use this point, which is the projection, which tells me the direction from which I'm accepting the H bond. Yeah. Please notice that life is never ideal. Yeah. So it means that in ideal situation, for the most convenient energy of the interaction, the H bond acceptor atom of the protein should be here. Yeah. In real life, it's a little bit shifted away, but still it will be a good interaction. So if I want to define not only the point but also the direction, I just click here and click feature again. And now I have this feature defined not only by the position, but also by the direction from which I'm expecting the interaction. Yeah? So this is the donor feature. Now let's define this atom. Yeah? And okay, we will again define it as a position and the direction where it comes from. Yeah. Okay, this is another one, and this time let's try to define it only by the position and not the direction. Let's be more tolerant. Yeah. So we have defined the H-bond donors, H-bond acceptors. What we should define more is the position of the aromatic ring. Yeah. So we can either use this point annotation. This is centroid actually because it's in the middle of the benzene ring. So it would tell me that the ring has to be here. If you want to specify the plane in which it has to be rotated, it means in a position favorable with the interaction of this phenylalanine, you should also use this vector projection. Yeah? So I have created these pharmacophore features based on H-bond donors, H-bond acceptors, and the aromatic interaction feature. All right, so these are the features. So you see I have created 7 features. And now I will use the protein itself to create the forbidden volume, yeah, forbidden space. So what I will do, just to be more clear, you can control the visibility of these features. So I select them and just hide them. Okay, they are still there, but just hidden. Now I will select the pocket So I go to select pocket. So pocket is defined like the ligand plus its closest surrounding. Yeah, so these are the atoms of the amino acid residues which form the binding site. And from these amino acids, I will create the volume, and especially excluded volume. It means forbidden volume. Yeah? So if you click on that, these gray spheres tells you that no atom of the ligand can be present in these gray spheres, within these gray spheres. If you want to be more tolerant, you can take the excluded volume and a little bit decrease the factor for the van der Waals radius. Yeah. So by decreasing this, you are a little bit more permissive, a little bit less strict. So you are basically allowing some, or counting with some protein flexibility, that the amino acid can back up a little bit when the ligand is being bound. Yeah. So now I have the combination of the pharmacophore features plus the excluding volume. And this would be my pharmacophore. Yeah? So this is how pharmacophore defined from a ligand complex looks like. Okay, now I'm ready to start the searching. And as I said, the searching using pharmacophore is quite fast. To give you an idea how fast it is, on a normal computer, you will be able to search tens of thousands of compounds in a minute. Yeah, so let's say 1 minute and 10,000 of potential ligands. So it's really much faster than docking. Yeah. Another thing I would like to point out, that even though if you have a model defined, you don't have to insist on all the features. Yeah? So for example, imagine a situation, you have constructed a model with 7 features plus excluded volume. You run the search, and your search on your defined library of potential ligands will end up with no hits, so 0 hits. So what you can do, you can perform partial match searching. Yeah? So by clicking on this button, you can say, okay, I have defined seven features, yeah, but I will be happy, all 8 together, yeah, 7 plus the excluded volume. And you are telling the computer, okay, I'll be happy if you don't find a ligand which satisfies 8 features, sorry. So fetch me ligands which satisfy at least 5. Yeah. So this is what you can do, what your solution could be when you don't have any hits using the most restrictive model of these eight features. Okay, when we are using partial match, we can also say to the computer, can tell the computer which features are essential for us. Yeah? So for example, let's think that this interaction, this H bond donor, I'll hide the volume. Yeah, so let's think this H bond interaction and this H bond interaction will be crucial for me. Yeah? So okay, I will select this donor feature, this acceptor feature, and I'll tell the computer these 2 are essential. Yeah? So essential sign will appear here, and it means now when we have set up like this, it means okay, search for ligands. I'm quite happy if the ligands which you fetch me do not fit all 8 features. It's enough to fit 5, but at the same time, I insist on that the feature 2 and feature 4 are satisfied, always satisfied. Yeah? So this is just an example how you can work with these pharmacophore models and how you can modify the models to get a reasonable amount of hits using your search. Okay. Let me go back to the PowerPoint presentation. So this slide just demonstrates the volumes. Okay, so this is the excluded volume. So the place which cannot be occupied by ligand because it's already occupied by atoms of the binding site of the target. Yeah? Quite on the contrary, in some situations, but you are not using it much often, is that you will define the occupied volume. For example, you have a pocket And you are on contrary to this situation, you are telling the computer, okay, find only ligands which have at least one atom in all these three occupied volumes. Yeah, so it means this area has to be occupied by at least one atom. This area has to be occupied by at least one atom, and this area has to be occupied by at least one atom. Yeah, so you can imagine these three as for example, three sub-pockets of the binding site. Yeah, and another volume you can use is the ligand shape volume. So you sometimes you are not concerned with the features of the ligand, but you just are looking for shapes. Yeah? So for ligands which have the good shape to fill the binding site. So different types of volumes. All right. So that was the creation of model in the situation when we have a ligand receptor complex. Now let's look at scenario number 2. We have the 3D structure of the target, yeah, but there in the target, in the binding site, there is no ligand. So what we can do, first we have to identify the binding site, yeah, because when there is no ligand, you cannot be sure where the binding site is. But you can get the information from the literature, for example, or you can use the site finder application, which is in MOE, to identify the potential binding sites. Yeah. Once you have the binding site, which you think might be the binding site, you will just observe how it looks like. Yeah. And for these observations, you can quite conveniently use the coloring features, which we practiced in the last seminar. So basically, you can create the map of the binding site and map some colors based on the properties of the binding site. And from that, you can derive the pharmacophore features. And of course, you can also use excluded volume, for example, yeah, because you still can define the volume which has to be excluded because it's occupied by the protein. And again, you construct the models, you evaluate the models, and if you are not satisfied, you go to this step, you modify your pharmacophore, changing the features and so on, adding, removing features, and you test the model again. So to give you a practical idea, yeah, imagine that we are looking at the binding site of a protein, and you see that we have no ligand here. Yeah, so we just suppose this is a binding site. We know it from literature, or the site finder app has suggested this might be a binding site. So what we can do, we can construct the binding surface of the binding cavities. This is the orange mesh, orange brown mesh, which you can see here. And then we can color certain patches of the mesh by different properties. So as an example, I have the coloring based on the preference for acceptor moiety, donor moiety. So acceptor would be red, donor would be blue, and hydrophobic preference would be blue. Yeah? So this is all together. Now let's split it into acceptors and donors, because you see there is not much preference for hydrophobic atoms. So let's omit hydrophobic and let's focus on donors and acceptors. Yeah, so acceptors first. So these red patches are telling me by the coloring where the protein is expecting H bond accepting atom from the ligand. Yes. Again, please remind yourself that this annotation is from the point of the ligand. So it means that, let's have a look. This red area, we would expect to have H bond acceptor in the ligand. Yeah. Is it correct? Let's check for us. Okay, here in protein, you have H bond donor. Here also you have H bond donor. So it's reasonable to ask for H bond acceptor to be here in this position. So I might consider that this really would be a pharmacophore feature for interacting with this receptor, but I cannot be sure because I see no ligand interacting within the binding site. Yeah? Similarly, here is a preferred site for H bond acceptor atom. Here is the preferred site for H bond acceptor atom. So I'll just choose based on my experience, based on my taste. I will choose some of these H bond acceptor features, and I will include them into my pharmacophore model. Now I'll do the same for H-bond donor feature. So again, these blue areas now tell me where the protein would like to have H-bond donor of the ligand. So let me check if it's really consistent. So for example, here we have the carbonyl oxygen of the protein backbone. Carbonyl oxygen, of course, acts as H-bond acceptor. So it means that in the protein, we have to have H-bond donor. So this is the H-bond donor in the receptor. And to have a good interaction, the donor can be either here, here, or here. So you can decide to take this feature as H-bond donor and put it into your pharmacophore. So you again select few of the H-bond donor features up to your taste, and you include them in your model. Plus, then you have the pharmacophore features based on the H-bond donors and acceptors, but of course you do not have to restrain yourself just to H-bond donors and H-bond acceptors as it was here. You can also use this coloring to define cations, anions, and so on. So this is just an example. Okay, so you have the features, plus then again you take the advantage of that you know the structure of the binding site, and you will define the excluded volume, which is always a good idea when you are working with the protein. All right, so we combine it together, and that's your pharmacophore model. And now we are coming to the last scenario. So the one which might seem the least favorable for you. So now in scenario number 3, we do not know the structure of ligand receptor complex. We do not know the structure of the receptor. We only know the structure of active molecules, active ligands. So what we will do in this scenario, this would be a ligand-based drug design method. So we will just take the individual active ligands. We will map the potential features, so the pharmacophore features, pharmacophore annotations, to the individual molecules, and then we will ask the computer to perform so-called flexible alignment. So flexible alignment or flexible superposition of active molecules. So this is the central term for this approach, flexible alignment. So what it is, the computer tries to align the active molecules in a way they would be sharing the highest possible number of the pharmacophore features. All right, so that's the flexible alignment, and when doing the alignment, it's quite similar to sampling the conformational space, which we talked about during the docking. So when doing the flexible alignment, you are not only changing the translation of the molecules, but also the orientation in the space. It means like rotation of the whole molecule. And most importantly, we are also changing the conformation, conformation of the ligands. So all these parts are being changed. Okay, so when you have the flexible alignment done, so we will determine the common features in the set of active molecules. So let's imagine that I have a set of 20 active compounds. I know from literature, from an enzymatic assay, that these 20 compounds are really active. I have done the flexible alignment, and now I see that 15 out of 20 compounds, for example, have a certain pharmacophore feature, let's say H-bond donor, in the same space. So probably 15 out of 20, that's good. So it leads to the finding or assumption that this pharmacophore feature might really be important for the binding. On the other hand, when you, for example, see that certain pharmacophore feature is present only in 3 out of 20 active compounds, that tells you probably that this feature is not necessary for the binding. So based on these thinkings and applications, you can come to a final pharmacophore. This time, of course, we cannot work with excluded volumes because we do not have any structure of the protein of the binding site. So we have just the common common features. Yeah, and then okay, we have suggested some binding modes. Pharmacophore models. Then we will be doing the evaluation, and iteratively we can change the model and improve it. Okay. Just brief note on how the flexible alignment, or if you want to, flexible superposition is being done. So these two slides are far too detailed, too much detailed for you. So you don't need to know the details. You can read it, but not a big deal. I just want to stress out two things. There are basically two approaches. You can do the superposition based on atoms. So what the software is trying to do, it's trying to put one atom on the other atom. So it's atom on atom superposition. Yeah, it's good for quite structurally similar compounds. Sometimes when your compounds, when your active ligands are structurally dissimilar, it's better to use the superposition of molecular fields. Yeah, what is it about? So in this approach, we are not trying to superpose atom on atom, but rather we will calculate a 3D potential grid, yeah, something which I described when I talked about the docking on the lecture. So we will create a 3D grid for some features, yeah? So for some property. Yeah? So for example, the positive charge. Yeah? So a map of positive charge, then a map of negative charge, map of hydrophobic feature preference. And then you will try to overlay not the structures with the atoms, but you will try to overlay the maps. Yeah? And based on the overlapping of the maps, you will have the superposition of the molecules of the active compounds. All right. So this is just a motivating figure to give you an idea how the flexible alignment might work. So this is taken from the commercial materials from this Cresset company, which is one of the producer of the software specialized in the flexible alignment. So you see, we had a set of active compounds, and when you did the flexible alignment, this is the result. So in some parts, in some structural features and in some pharmacophore features, the molecules are the same. Yeah, so for example, from this superposition, I might get the idea that this hydrogen bond acceptor is important for binding because it's in most of the ligands and it's nicely aligned. Same situation for this one, for this H bond donor, and so on. On the contrary, for example, here we have two hydroxyls. Yeah, I cannot know if the hydroxyl here works as an H bond donor or H bond acceptor. But anyway, we have the hydroxyl only in how many? Let's say 2-3 compounds out of these 20 plus compounds. So this feature might not be that important. So to my pharmacophore model, I would include this feature, probably this feature, maybe this aromatic feature, and that could be all. Yeah, definitely in the spaces where the ligands are dissimilar, we will get something like this. Yeah, so from this mesh of compounds, mesh of fragments, you can tell that there are no repeating features in these areas, at least at the first sight. So you will not define any pharmacophore feature in this area. Okay, an important note here is that when you are trying to produce a pharmacophore from the ligands, you should always try to have structurally diverse ligands. Why? Because if you use just one structural type, you might be quite misled. Yeah, you would produce the pharmacophore which is optimal for certain structural type of ligands, but you might miss the other ligands of different structure. So, for example, we have a GABA receptor, yeah, and we have different ligands for this receptor. We have a benzodiazepine. This is in the blue, white sticks, yeah? And we could easily get from the literature many benzodiazepine structures which are ligands of this GABA receptor. But what would it lead to? Yeah, we would end up with 20, 30 compounds which would be aligned exactly in the same manner as this white compound. And from that, I would think to myself, okay, all ligands, but note they are all benzodiazepines, have H bond acceptor here. Okay, I'll put it to the pharmacophore. And I would also think all the compounds have H bond donor / acceptor here. So I would also include this feature into the pharmacophore. But when you compare with other active ligands, which are of different structural class, so the green one here is non-benzodiazepine ligand, of a different, very different structure. What you can see, okay, this feature, which I took from the benzodiazepine, is also present in this non-benzodiazepine ligand. Okay, the positions are not exactly the same, but they are very similar. Remember, we always have some tolerance. So this feature, H bond acceptor feature, is here both in the benzodiazepine class and non-benzodiazepine class. So probably it's very important for the binding when you have it in different ligands. Similarly, here, this oxygen atom here and here is on similar place. So I will make an assumption that it's important for the binding, and I will take it to the pharmacophore. All right. On the contrary, what I see here, that this pharmacophore feature is present in the benzodiazepines, but not in these type of ligands. So it's not necessary for the binding, obviously. So I will probably choose not to include in the pharmacophore module. Similarly, this nitrogen atom is present here, but not present in the benzodiazepine. So I will not include it in my pharmacophore module. So that's a note on the importance, how important it is to have structurally diverse ligands when constructing the pharmacophores. And this holds especially true for the situation when we are constructing the model from the ligands. It also holds true when we are constructing the model from the ligand receptor complexes. So when you have different ligand receptor complexes in the PDB database, that's scenario 1, you could always, or it's a good idea to try select the complexes which have structurally different ligands. All right, so then we just choose the pharmacophore features, which we want to include, and the model is constructed from these. Okay, so pharmacophore model from active ligands. I have described the greatest risk, which is that if you use structurally uniform ligands, you will end up with pharmacophore models which are optimized for that structure, but not for any other structure. Probably. Another problem which I should mention is the conformation, actually. So I said that when you are doing the overlay of the active ligands, you are changing the conformation. But this might be a problem because you might, in the overlay, the computer might use a conformation which is, for example, energetically unfavorable. So you have a conformation, but the conformation in which the ligand really binds to the binding site might be different. So this is what needs to be bear on mind, these problems. Okay, this slide is just to give you an information that there are actually many automated softwares which can do the pharmacophore identification and then do the pharmacophore-based search for you. So that's all I want to say here. All right, this automatic identification processes should be automatic, of course. So they have to decide. Let's say if you have 20 active ligands and you want to do the overlay, structural overlay, flexible alignment, you have to choose the template ligand, so which will be the first one, and all the other ligands will be aligned upon the first one. So it's quite important to choose which should be the reference ligand. So good idea, a good tip is to, of course, start to have the reference ligand as the one which is most active and also the most rigid. Because, okay, let's imagine the situation that this ligand on the left and this ligand on the right are of similar activity. So I could have my template as this one or this one. But with this one, this is much more flexible. You see the flexible linker here. So I cannot be quite sure about the correct conformation. So I don't know to which conformation I should be overlaying. But this ligand is quite rigid due to this cycle which is formed here. So basically there is no conformation flexibility here, just a little bit in this cycle and 1, 2 rotatable bonds, and that's all, compared to this. So this is much less flexible, so I'm much more sure about how the conformation, the active conformation, could look like. So I will choose this one as a template, and I will overlay this, which is of similar activity but more flexibility, onto this one. All right. So this concludes the part about Pharmacophore-based searching. Just one last note. I told you that you can use the Pharmacophore-based searching as a quite fast method. So you will probably use it in the beginning of your HTVS, high throughput virtual screening scenario. It means that you can actually use the outputs as Pharmacophore-based searching as the input for docking. So for example, let's say in your project, okay, we will not start with hundreds of thousands of compounds because that would be, you would need too much time to run the simulations. But okay, if you will in your project start with 10,000 compounds, first you could probably do the Pharmacophore-based searching. Yeah, it will be quite fast, and this Pharmacophore-based searching will identify ligands which might fit into the binding site, and the best ligands identified by the Pharmacophore searching, you will use them as an input for molecular docking, for example. Okay, so this is the first part of the lecture. So I briefly switch to the main window if there are some questions. It's probably not the case. You can always ask on your microphone. All right. So let's go to the second part, which will be significantly shorter. Don't be worried. So, and this is about similarity searching. So when you want to identify new potential ligands of your receptor, you can just rely on structure similarity. So the idea is when a ligand is structurally similar to your confirmed inhibitor, then probably your ligand could be inhibitor as well. So we want to confirm or search structurally similar ligands. This is usually done using so-called molecular fingerprints. Yeah? So now we will be talking about molecular fingerprints. And once we have defined or calculated molecular fingerprints, we can use them to compare if two molecules are similar or dissimilar. Okay, just to set these molecular fingerprints into the framework. So molecular fingerprints belong into the group of so-called molecular descriptors. Yeah, molecular descriptors. This is just a very wide term. So molecular descriptor is basically anything, any numbered value which describes the property of the molecule. So you can have very simple molecular descriptors which you can calculate from 1D structures. You just need to know the type of atoms and the number of atoms which are present in the structure, and from that you can calculate, for example, molecular weight. Yeah? For certain types of descriptors, which we call 2D descriptors, you have to know the 2D structure. It means how the atoms are connected. Yeah? This is what we call also a topology of the molecule, how the atoms are connected. So 2D structure or topological descriptors. Yeah? So topological descriptor or 2D descriptor could be calculated log P or total polar surface area, topological, if you want to, topological polar surface area. Also the number of H-bond donors, H-bond acceptors, you calculate them from 2D structure. All right. So that's it. Some of the descriptors are more complicated, so you should compute them from 3D structures. Yeah, so this we call 3D descriptors, and this almost a synonym is topographical descriptors. All right. Those molecular descriptors are very heavily used in QSAR methods. QSAR methods are methods when we try to find the mathematical equation which predicts the activity of a compound based on the values of certain molecular descriptors. Yeah? So molecular descriptors are inputs, and output is the prediction of the activity of the compound. The softwares which we are using today can calculate up to or even over 3,000 of descriptors for each molecule. Yeah, 3,000 of descriptors. So just to give you an idea how broad the term of molecular descriptors is. Anyway, today we are supposed to talk about molecular fingerprints, and molecular fingerprints belong to topological descriptors, which we can derive from 2D structures. So you need the information about the connections in the molecule. In the final test, we are asking for these two types of molecular fingerprints. So there are knowledge-based fingerprints, or the synonym is structure key fingerprints. And then we have information-based fingerprints, which are hash key fingerprints. What is the difference? Maybe to understand these terms, you should remember rather the right equivalent of these names. So in structure key fingerprints, the idea is that to calculate this type of fingerprint, we need to predefine a so-called vocabulary set. So we predefine a set of let's say fragments, yeah, vocabulary of fragments, and then we will be looking if certain fragment is present in the molecule or not. Yeah. On the contrary, with the second type of fingerprints, which are called hash key fingerprints, the idea is that the fragments of the molecule are not defined in advance, yeah? So they are not in a vocabulary, in a library, but they are being calculated on the flight as the molecule is being torn to pieces, as I will show you. Yeah? So the difference is that in these fingerprints, you have the fragments defined in advance. In this approach, hash key fingerprints, you calculate the fragments as you portion the molecule. All right. So to give you an example, yeah. So knowledge-based fingerprints, structure key fingerprints. Yeah. So imagine, for example, that one of my defined fragment is the carboxamide moiety CONH. Yeah. So that's present in my vocabulary. Then another term in my vocabulary is this imidazole ring. Yeah. And I can define as many fragments as I like to. Yeah. And then converting the molecule to the molecular fingerprint. Yeah, so this is the molecular fingerprint, which is a bit information. You just check, you just test if the certain fragment is present in the structure or not. If the fragment is present, then the value of the bit is 1. If the fragment is not present, then the value of the fragment is 0. All right. On the right, we have the example of hash key fingerprints, yeah, which are specific in that way that the fragments are not defined in advance, but you just do the fragmentation of the molecule, and by the fragmentation, you define the fragments, which you then test for the presence in the molecule. I will give you an example on the next slide. So in the test, we are asking you, if I remember correctly, about Fingal fingerprints and Morgan fingerprints. Yeah? These both two belong to the hash key group of fingerprints. Yeah? And let's see now how the structure is being partitioned, yeah, into the fragments. Yeah, so firstly, we need to define the atom where we start from. Yeah, so this is quite difficult to do, but there are some algorithms optimized for that, so it can be done. So the starting atom, the nitrogen, is this nitrogen. Yeah, and then I'll enlarge a little bit. Okay, so this is the nitrogen. So this is the first atom. Then we go to the second atom. Yeah? So we can go either to the left, so it will be nitrogen, double bond, carbon. This is it. Nitrogen, double bond, carbon. Yeah? Or we can go to the right. We will have nitrogen, single bond, carbon, which is here. Nitrogen, single bond, carbon. And these are the fragments which we are defining on the flight as we portion the molecule. Then we will go to the second layer. Yeah? So we go from here, but to the distance of 2 bonds. So we will have, nitrogen, double bond, carbon, single bond, nitrogen. Yeah? This is it. Nitrogen, double bond, carbon, single bond, nitrogen. Or we can go to the right. Nitrogen, carbon, double bond, carbon. This is it. But also we can go in this direction. Nitrogen, carbon, single bond, nitrogen. This is it. Nitrogen, carbon, single bond, nitrogen. And by this, we are going to the layer of 2, 3 atoms, 4 atoms, and so on. And we are defining the fragments. Yeah? So these are the fragments which are being defined. And then we just test if the fragments are present in the molecules or not. Yeah. So of course, all the fragments which I have defined by portioning of this molecule will be present in this one, but they will not be present probably in all molecules, yeah, in the other molecules. So this is the Fingal fingerprint approach. Morgan fingerprints is very similar. Again, we need to set a starting atom, which will be this one, this carbon. And then we again move in the layers, but this time not like linearly by bond, but in circles. Yeah, so this is the first atom. Then in the next layer we will have all the first atoms. Yeah, also all the second atoms. So yeah, so this would be this one, this, and this. Then we go to the next layer, and we are increasing the size of the circle and creating the fragments on the fly. Okay, and this is almost the last slide. So here I will demonstrate how the fingerprints, once we have them, can be used to perform the similarity searching. Okay? Because that's why we produce the fingerprints, to be able to quickly compare the similarity or dissimilarity of two structures. All right, so let's suppose we have a set of fragments. It doesn't matter if we have defined them in advance. That would be the first type of fingerprints, or we have defined them on the flight. Doesn't matter now. Just let's observe if these fragments are present in molecule 1 and in molecule 2. So benzene ring is present both in molecule 1 and molecule 2. So it will be bit value 1, bit value 1 in both cases. Carboxylic moiety also present in both of them, 1, 1. Isopropyl moiety not present in any of these, 0, 0. Hydroxyl is present in both. Yeah, be careful that it doesn't have to be hydroxyl in the exact sense. It can be just, yeah, we are talking about atoms. So this, we know that it's not carboxyl, it's not hydroxyl, it's carboxyl, part of carboxylic function, but still for the similarity searching it's the same. So hydroxyl. Yeah. And also note that this is not about the number. Yeah, so here we have 1, let's say hydroxyl. Here we have, let's say, 2 hydroxyls, but this is not about the numbers. This is just 1 is present, 0 is not present. That's all. That's true or false situation. Okay, so then we do the comparison for all the defined bits. And then based on this, when you have 2 fingerprints, we can use some mathematics, some called metrics, to compare the fingerprints. Yeah? So one of the most heavily used metrics to compare 2 molecular fingerprints is the Tanimoto coefficient. Yeah? So this is an important term, and we are asking this in the final examination test. So Tanimoto coefficient or Tanimoto index is defined by this formula, yeah? But more important for you is to understand the meaning. So in theory, the Tanimoto coefficient can have values from 0 to 1, when 1 means that 2 molecules have exactly identical fingerprints. Be careful, this does not mean that the molecules have to be necessarily structurally identical. Yeah, because we can imagine the situation, because this depends on how you have defined the fragments. So we can imagine 2 structurally diverse molecules, similar but diverse, yeah, not similar but not equal, I mean, which have TI, so Tanimoto coefficient equal to 1, so which have the identical fingerprints. Yeah? So identical fingerprint does not mean identical structure necessarily, but very similar structure. Yeah, in a practical life, there is a certain value of Tanimoto coefficient 0.65, that you should remember. And if you calculate the Tanimoto coefficient and it's 0.65 or higher, it means that the compounds are sufficiently similar for the purposes of computer-aided drug design. Yeah? Of course, if you want to have more similarity than the normal cutoff value, then you can search only for compounds which have Tanimoto coefficient larger than 0.8, for example. Yeah. All right. Let's have a look at the formula, how Tanimoto coefficient is being calculated. It's quite simple. So here you have the formula, and let's define the meaning of the letters. So A is the number of bits which are set to 1 in both compounds, which we are comparing. Yeah? So this is this situation, 1, 1, 1, 1, and 1, 1. So 3 bits are set to 1. So 3 bits are true in in both compounds. B is the number of bits which are true in compound 1, but not true in number 2. So we are looking for this situation. This is this one. Yeah, true in 1, false in 2, and this one, true in compound 1, false in compound 2. So we have number 2. And C is the opposite situation, bits which are true in compound 2, but at the same time false in compound 1. Okay, this is not the case, not the case. So there is none, so 0. And if you put this into the formula, yeah, you will have like this expression, which leads to 0.6. Yeah, so the Tanimoto coefficient when comparing these two fingerprints of these two compounds is 0.6. So it's close to the value which we consider similar. And if you look at the structures, you must agree that the two compounds are really quite similar. Yeah, we have by the way, this is acetyl salicylic acid, of course, and this is salicylic acid. Yeah, so very similar compounds. Yeah, so Tanimoto coefficient is the metric to compare two fingerprints. The important thing is that you can compare only the same fingerprints with each other, yeah, because there are different numbers and different fingerprints which you can calculate for each molecule. So if you want to do comparisons, you have to use the exact same algorithm to calculate the molecular fingerprint, and then you can compare. Okay, similarity searching based on molecular fingerprints is even faster than pharmacophore searching. So if you want a method which will quickly discriminate between similar and dissimilar compounds compared to your confirmed ligand, for example, confirmed inhibitor, then this is your choice. So talking about the speed of the process, pharmacophore searching is fast, but similarity searching is definitely even faster. Yeah. So ordered by the speed, similarity searching fastest one, pharmacophore searching quite fast, and docking is the slowest but the most precise. Okay, so to sum up this presentation, we have been talking about pharmacophores and how they can be used for searching of new potential ligands. So from that, you should definitely know the definition of pharmacophore. You should know about what kind of features we can define, that we have atom annotations, vector annotations, centroid annotations. You have to know how we can construct the pharmacophore model and how we can use it for searching. Then we are talking about molecular fingerprints. So you should know the basic principles, that the molecules, their structure is somehow transformed or encoded, if you want to, into bits of information. Yeah? And there are two types of molecular fingerprints. One is typical by the fact that the fragments are predefined, and the other one is typical by that the fragment is not defined and is calculated on the way as the molecule is being partitioned. Yeah, Tanimoto coefficient, definitely an important metric to remember, and we are asking this in the test. So this lecture should give you an idea which methods you can use to identify potential ligands if you want or if you need to use a faster method than molecular docking. So this, I think, concludes my lecture. So thank you for your attention. I will wait here for a few minutes in case you have any questions. And let me remind you that next week, Friday, we have the seminar, which is obligatory for those ones who have enrolled the subject. Okay, thanks for attention, and I'm ready for your questions. If there are no questions, then thanks for attention once again, and have a nice weekend.